Hi everyone, thank you very much for coming, and thank you to all the organizers for inviting me to give this talk. My name is Abhishek Kumar, I am from IIT Jammu. The title of my talk is Resonant Edelstein and Inverse Edelstein Effects, Charge to Spin Conversion and Spin Pumping from Chiral Spin Modes. This work recently got published in PRB, which is this year, and I should also mention that this work is a contribution to PRB as a special issue in memory of Emmanuel Rashpa, who passed away last year, leaving behind the legacy, lasting legacy, which inspires a variety of research in spintronics and condensed matter physics. So let me start by acknowledging my collaborators, starting with Mosde, who is a PhD student at Concordia University, then Saurabh Maiti, who is Mosde's PhD supervisor at Concordia, and then my own PhD supervisor, Professor Dimitri Maslov at the University of Florida. Saurabh, he is a long-term collaborator. He happens to be a postdoc in our group at Florida when I was a PhD student there, and he went on to become a faculty at Concordia later on. Okay, so as you see, the title is quite long, so let me try to break it down, starting with the discussion of Edelstein and inverse Edelstein effects. So what are these? So let's consider that we have a spin split Fermi surface, all right, and the Fermi surface is such that the helicity of these two surfaces are opposite to each other. For example, the outer surface has positive helicity. If I consider that, then the inner one has opposite negative helicity. So I'm sure by now you must have guessed what kind of effect I am talking about here, but the context will be the context will be clear very soon. The point that I am trying to make is that this is the equilibrium situation, and the average spin polarization for this case is 0. Right? Now I apply electric field. All right. When I apply electric field, the Fermi surfaces shift. Okay, that's because first of all, under the influence of electric field, electrons accelerate, but then there are scattering events which relaxes its momentum, and in the steady state it's merely the small shift of Fermi surfaces that happen, when there is shift in the Fermi surface, you see there is finite polarization that is induced in the system, and that is nothing but Edelstein effect. Then there is reciprocity, according to Onsager reciprocity theorem, there is inverse Edelstein effect as well, which is nothing but electric current induced by non-equilibrium spin polarization. Now at the heart of it, what is there, why this is happening? This is due to spin momentum locking. Okay, so here under the influence of electric field, it's the momenta of electrons that shift. Right, so and that shift in momentum translates to the induced spin polarization. So somewhere spin and momenta are connected with each other. So that's why spin momentum locking. Now, where do you realize this? You realize this in, for example, two-dimensional electron gas. Right, you have, let's say, gallium arsenide, aluminium gallium arsenide heterostructure. At the interface you have two-dimensional electron gas. Now the motion of electron across the interface is confined because there is confining potential that leads to very strong electric field. Now look, when you look at this electric field in electrons frame of reference, electrons will experience effective magnetic field according to Maxwell's equation. So that's E cross V over C squared, and that is nothing but effective magnetic field which couples to electronic spin, giving rise to splitting in the spin space, something like this. All right, when this k square over 2m term, in addition to Rashpa spin orbit coupling. So yeah, so that's where you have, and that's where the spin orbit coupling that arises, that's called as Rashpa spin orbit coupling. So in combination with parabolic term, there is a shift of, there is a splitting of bands, and the Fermi surface looks like this concentric circles which I showed you earlier. So So all these things are conventional. So I was talking about all these responses so far has been talked about. That's DC response. You apply static electric field, you have static spin polarization induced, and vice versa. But what happens in the dynamical regime? That is something which I am interested in this work. I have oscillating electric field, you have oscillating spin polarization, and vice versa. So that's linear AC Edelstein and inverse Edelstein effects. That is what I am trying to talk about. What about the resonance effect? That will be clear as I go on in this talk. Okay, now second key piece of this title is chiral spin mode. The other two, charge to spin conversion and spin pumping, these are applications that will be that I will discuss towards the end when I will be finishing the talk. But let me first explain what chiral spin modes are. So here I'm talking about spin orbit coupling in systems with broken inversion. So broken inversion in the sense, as far as Rashpa spin orbit coupling is concerned, it's the inversion symmetry breaking across the interface. So let's call that as Z direction. So you have these two semiconductors across the interface. You have strong symmetry breaking field or electric field, and so that symmetry is broken because you have two different environments, gallium arsenide and aluminium gallium arsenide, for example. Okay, so these are the two examples. So I already told you about semiconductor heterostructures. Another example is graphene, but not freestanding graphene. But if you adsorb graphene on transition metal dichalcogenide substrate, there is a new type of Rashpa and Valley-Zeeman spin orbit coupling that are induced in it. On its own, graphene does not have Rashpa and Valley-Zeeman, but because of this substrate, a sizable strength of Rashpa and Valley-Zeeman in the range of milli-electron volt that is induced. And in semiconductor heterostructures, in addition to Rashpa, there is Dresselhaus term. And the crucial difference between Rashpa and Dresselhaus is that Dresselhaus is due to bulk inversion asymmetry, whereas Rashpa is due to surface inversion asymmetry. So if you take an example of gallium arsenide, then you know that it's a non-centrosymmetric crystal. So in the bulk, the inversion symmetry is broken. So there is bulk Dresselhaus term, but at the surface, you have surface Dresselhaus term also. Then you are placing the system in a vacuum. So of course, at the surface, you have Rashpa term also. But when you have silicon semiconductor, you place that in vacuum. At the surface, you have Rashpa, but you do not have Dresselhaus because silicon, that's a centrosymmetric crystal. So that's the origin of Rashpa. And Edelstein effect that occurs or that arises due to Rashpa and Dresselhaus both. So it depends what kind of spin polarization that is induced in the system. The direction of spin is important. All right. I told you about spin orbit coupling. Now the interplay of these are electronic systems. So of course, the electron-electron interaction is quite generic in these systems. Question is, what is the interplay of spin orbit coupling and electron-electron interaction give rise to? So it gives rise to many things, but one thing that I am interested in, that is collective excitations in the spin sector, also known as chiral spin modes. Physically, that means oscillations of magnetization in the absence of external magnetic field. So we understand the role of magnetic field. You apply magnetic field, you have magnetization. So you have oscillation of magnetization when you have the interplay of external magnetic field and electron-electron interaction. You have collective modes there also, but here the situation is different. It is arising in, the modes are arising in the spin sector mainly due to spin orbit coupling. Okay, and the chiral here, that is mainly due to the chiral texture of spin orbit coupling, chiral texture of spin that you get from spin orbit coupling. Right. So the question that I am asking is, what happens to Edelstein and inverse Edelstein effects at chiral spin mode frequency? What is the role of interactions, and what are the advantages of this work? So these are the references. The first one is something, that's the main work that I'm going to talk about here. The main message is based on that. These are the supporting references about collective modes. You can refer these three works. That's a review paper, so better you start from here. And then these are other references. If you want to dig deeper into the subject, these will help you. Okay, now let me go into a bit of details of collective modes in two-dimensional Fermi liquids. It's basically in one slide, I am simply going to give you a crash course of Fermi liquid. So it's a phenomenological theory proposed by Landau, which states that strongly interacting fermions near the Fermi level can be mapped onto weakly interacting quasi-particles. And in the process, the mass of electrons, the magnetic moment, etc., these are renormalized due to interactions, and then that gives rise to many interesting effects. Now coming to collective modes, so of course these are the two systems that I want to work on. Before talking about collective modes in the spin sector, I hope we all are aware of what happens in the charge sector. In the charge sector, we have plasmons. Right, plasmons are nothing but quasi-particles arising due to oscillation of free electron gas density. So in both these systems, it has been found a long time ago that the plasmon spectrum that disperses as square root of q, where q is momentum transfer, and this result is applicable at in long wavelength approximation where q is small. Now, what happens in the spin sector? The conventional case, due to external magnetic field, we have Stillin-Leggett mode, also known as spin waves, and then we have chiral spin modes arising due to spin-orbit coupling and the interplay of it with electron-electron interactions. Only difference is that these are in these two systems, there's a big difference because we have different types of spin-orbit coupling. Dressel-House coupling, that is not present in graphene because, of course, graphene is centrosymmetric. Okay, let me give you a bit of details about collective modes in the spin sector. Starting with spin waves, physically it corresponds to, so you apply magnetic field. Now electronic spin starts processing around this magnetic field. Now when you do not have any interaction, these spins process independently. Okay, now you turn on interaction, they start talking to each other, and then they start processing in phase. There is a associated frequency called as collective mode frequency. Now here one can see that otherwise parabolic band splits into two spin up and spin down bands, and q equals to 0 transition is possible, unlike in the case of charge sector where plasmons are present. Here you only have the transition, the particle hole transition at the expense of finite momentum. But in this case, you have within infinitely long wavelength approximation, which is q equals to 0, you have transition between two spin split bands possible. Now that tells us that the end point of the condition, so okay, this is at q equals to 0, consider q equals to 0 case. You see that this single particle transition, that's the Zeeman energy, and this is also renormalized by Landau parameter, that's electron-electron interaction. So end point of the continuum is simply a point. And then there are collective modes lying below the particle hole continuum. So there are infinitely many modes, only the within S wave approximation, that is for isotropic interaction, omega naught only, that is ESR, that is electron spin resonance, or NMR, nuclear magnetic resonance active. Okay, and then at finite q, these modes disperse. What happens to chiral spin modes? That is, take an example of two-dimensional electron gas, that's the Hamiltonian. Here, that's the band splitting. Again, near the Fermi surface, when you assume spin-orbit coupling to be small compared to Fermi energy, near the Fermi surface, vertical transitions are possible. That is, q equals to 0 transitions are possible. That's the spectrum of collective modes. Here I have considered external in-plane magnetic field also, but let's first try to understand what happens at field equals to 0. Again, q equals to 0, S wave or isotropic interaction that I am assuming. So here you see that there are up to 3 collective modes. At field equals to 0, 2 modes are degenerate. That's because there is rotational symmetry in the plane, and Rashba does not break that rotational symmetry. So you do not have distinction between x and y directions. So the oscillation of magnetization along x and y, it's the same. That's why modes are degenerate. And then there is third mode, that is out of plane oscillation of magnetization, that is non-degenerate. But as soon as you apply magnetic field in plane, there is time reversal symmetry breaking, and these modes, the degenerate modes, split. because yeah, and at some critical field, these two modes run into the continuum, whereas the third mode that grazes the continuum all the way until the gap closing point, and then appears again, eventually adiabatically connecting to spin waves, and that is what it should happen at very large magnetic field. So this is not only at the level of theory, but it has been observed experimentally also. Well, actually, it was first observed, and then we tried to explain the experiment. Now, in the experiment, I mean, they do inelastic light scattering, that is Raman scattering, with cadmium manganese telluride, which is a quantum well. So that's two-dimensional electron gas, of course. You apply in-plane magnetic field, and there is a sharp resonance that you see here, sharp resonance, and that's the continuum. Now, why? So in here we predicted up to three collective modes, but here there is only one mode, mainly because the external magnetic field that they apply, that is 3 Tesla, that is quite large compared to the intrinsic spin orbit magnetic field that is there in the system. So basically the signal is coming from this region. That's why only one mode, and the continuum that is over there. Okay, coming to graphene. Chiral spin modes have not been observed in graphene, so that's why that is again another motivation of studying cross response that I am going to talk about. So very quickly, that's the Dirac term of the Hamiltonian, graphene Hamiltonian, low energy Hamiltonian to be specific. Then there is Rashba term and Wally-Zeeman term. Rashba term, okay. Just ignore Wally-Zeeman term for now and just see the spectrum of Rashba. So what you see that conduction and valence bands both split in the spin sector, and resulting into various transitions, possible transitions from valence bands to conduction band. Now within conduction band, it's fine, it's low energy transition, but from valence to conduction band transition is of the order of 2 mu, which is quite large. So Fermi liquid, within Fermi liquid, you will not be able to capture that. So what we do, we integrate out valence bands and work only with the effective conduction band, and that is how the downfolded Hamiltonian looks like. So this is the Rashba term, and that's the Wally-Zeeman term. So later on I will take into account both Rashba and Wally-Zeeman, but just for the purpose of demonstration I just showed you the spectrum, single particle spectrum only for Rashba coupling, but Wally-Zeeman also it looks similar. I mean something similar to this one. So next step is to analyze chiral spin modes using two-valley Fermi liquid theory and predicting those modes in electron spin resonance and electric dipole spin resonance spectroscopies. So that's the result. For collective modes, we found that the single peak in the non-interacting case splits into two for graphene, for the case of graphene, and that splitting is mainly because graphene has two valleys. In two-dimensional electron gas, it's not the case. So the mode never splits because it's the single valley thing that we work with. Physically, this corresponds to oscillations of uniform magnetization and valley staggered magnetization. Okay, so far, whatever. So these were all the background of collective excitations in the spin sector. Now, what about response functions? So let's talk about direct and cross responses. The cross response is the main thing about this work. So by direct response, I mean that you apply magnetic field, you measure magnetization, and spin susceptibility is the response function. Similarly, you apply electric field, you measure current, and optical conductivity is the response function. But what about the cross responses? You apply electric field, you also have magnetization induced in the system. That's dynamical Edelstein. You apply magnetic field, you also have current induced in the system. That's dynamical inverse Edelstein effect. Okay, so that's a new work. That is something which we realized. We verified that the resonances in direct and cross responses coincide. Now you may ask, then what am I doing here by doing this calculation? So what's the advantage of the study of cross response? The answer is it's the observability of response functions. So as I told you that so far chiral spin modes have not been observed in graphene. So by cross response study, we are proposing a way to observe these chiral spin modes. So this is the result of monolayer graphene. You see that that's the direct response. You apply electric field, that you measure current, and then you apply magnetic field. That's a cross response. Magnetic field, measure current. This is the magnetization. That's the cross response, and that's the direct response. The point is, you can observe that electrically driven responses, these two, whether direct or cross, that is always large compared to magnetically driven ones. Now, why is it so? If you compare the response functions, you immediately realize that there is a Compton scale. There is a Compton wave vector which is large compared to Fermi wave vector. A simple reason is that Compton wave vector, that is mass times speed of light. Okay, and that's why it is small. So that's the reason why electrically driven responses are stronger compared to magnetically driven ones. Now I am claiming that detecting chiral spin resonances in cross response is favorable. Why is it so? That is mainly because if you apply electric field, you measure current. But there is also Drude contribution to optical conductivity, and then even at finite frequencies, the Drude tail smears the effects arising due to spin orbit coupling. Okay, and that's why the cross response is better. You instead measure the magnetization, and from there you will be able to see the effect. And why only electric field, electrically driven response that I am talking about? Mainly because of this reason, the signal is stronger. And that's the reason. Okay, so that's the now I'm making connection with the experiment. So detecting chiral spin modes via resonant inverse Edelstein effect. So let's say we have normal incidence, electromagnetic wave, then I have magnetic and electric field components are in the plane. Now when you have magnetically driven response, because that's inverse Edelstein effect, you have current induced current will be along the direction of electric field. Now that will compete with the direct response, right? And the direct response, of course, there is a Drude tail which will smear the effect. Now what you do, instead of normal incidence, you bring the light at grazing incidence with the electric field component perpendicular to the plane, with magnetic field component only in the plane. Then what happens? You have induced current that will be in the plane, specifically along the direction of this incident wave, and that's where you have full access to the cross response, and it is certainly easier to measure. Speaking of Edelstein effect, the normal incidence will work. You can have this electric field induced magnetization that will be along the direction of magnetic field, but I told you electrically driven responses are very large compared to magnetically driven response, so the direct contribution will not affect much. So that's how so that's the that's a proposal to see Edelstein and inverse Edelstein effects in these system. So that's the full result of current, and you see this is Drude Drude contribution. That's the electrically driven response, still direct response. It's called as electric dipole spin resonance. That's the resonance is there near the Rashpa term. And then there is cross response, magnetically driven current. You see that the prefactor is directly proportional to Rashpa term. It does not depend on Wally-Zeeman coupling, because Wally-Zeeman does not take into account the spin momentum locking. So when you have Rashpa equals to 0, even though you have Wally-Zeeman, you will not have any cross response. Yeah, no, I'm about to finish. So okay, and now coming to the applications, charge to spin. So 5 minutes of talking, or it's for question?
5 minutes of total 5 minutes. So
oh, okay. Oh, all right. So let me just quickly tell you about this. Spin pumping probably I'll not be able to cover, but okay. In most of the literatures, it's the static figure of merit is something that's a measure of charge to spin conversion, and that's the definition. That's the cross response. And now this is static because frequency equals to 0 I'm talking about, and that's the direct response. So in two-dimensional electron gas, it has been observed that when only the bottom band is occupied, and the dimension of this is inverse velocity, so typically it is multiplied by Fermi velocities, and then see the number, compare the number. So when only bottom band is occupied, this number was obtained to be roughly 0.1, between 0.1 to 3. Then what happened? What happens that when you increase that, because of course accessing this regime is very difficult. You have to control the doping, which I'm sure experimentally you find it you may struggle doing that. If not, then very good. But VF eta that was found to decrease as doping increases, right? But so that is one aspect which may be a limitation of static figure of merit. What about if you consider dynamic figure of merit? In this case, it was found that even for large doping limit, the enhancement in the VF eta that was found. So that's the result. In addition to this enhancement in the large doping limit near the chiral spin mode frequency, also there is 4 orders of magnitude enhancement, and that's the effect of interactions, this peak for a particular number that splits into 2. So this is the architecture of ultra fast spin pumping, which is it's like you have ferromagnet layer and normal layer. So, typically that the spin is pumped in the normal layer without pumping any charge current. So we have provided architecture ultra fast spin pumping in the terahertz regime by all electrical means and also by using magnetic field. So that's these are the summary of my, this is the summary of my work. I talked about direct and cross responses. I hope I tried to convince you that measuring cross response is favorable, and then charge to spin conversion. Sorry, I did not tell you a bit details of ultra fast spin coupling. So thank you for your attention.
Thank you. Thank you. So now the session is open for questions. Any questions?
Thank you for the nice talk. I was just curious to know, when you were talking about this extraction of this effect, when you are considering the effect of the dynamical effect, say the magnetic field is actually creating this transverse
yes,
effect of this
yeah.
thing. I was just wondering, in terms of experimentally looking at it, so suppose we take a particular pulsed energy source or something like that, is it possible to convert the amount of, because the magnetic field strength of an electromagnetic wave is very small.
That's right, yes.
So is it possible to kind of give some kind of a rough numbers in terms of what kind of pulse energies one would really need? So suppose one is driving through terahertz pulse.
Yeah, so the electric field, or maybe I know about electric field, maybe megavolt per centimeter. If and that is something I know papers.
Megavolts is possible.
Yes, that's possible. So I think that will work here. So yeah, we have discussed this experimental prospects also with existing literature.
Thanks.
Okay, any more?
So my question is related to the detection of this chiral spin wave. So there are basically you have to first conserve the energy, right? When you light or neutron, whatever, it interacts with the system. The second, the wave vector conservation. So it has certain q vector, right? And also because of its precision, the chirality, it also has its own momentum, angular momentum.
Okay.
So how this momentum conservation works here?
Yeah, I mean, it works very well. So for example, if I talk about electron spin resonance or electric dipole spin resonance, in these cases, these are all elastic effects. So the momentum and energy conservation works perfectly well. But however, if you talk about Raman spectroscopy, that's where the energy conservation will not work. But again, the difference, the Raman shift, that is something that tells you about the energy of collective modes. But as far as this work is concerned, everything works quite well. I mean, the conservation of momentum and energy.
Very interesting talk. So what is the origin of chirality here?
It's the spin orbit coupling. So spin, I mean, Rashpa and Dresselhaus, this thing, and in graphene also mainly Rashpa, not Valley-Zeeman. But there is a role of Valley-Zeeman also in this case, but it's the Rashpa coupling. Yeah. That's the
That's enough to induce chirality, the
yes, yeah.
excitations.
Yes, yeah.
When you say chiral excitations, what can you like tell us what exactly are you little more about that? Like what kind of excitations are there?
It's mainly the spin texture that is what I refer to this by. Like in magnetic field, you have spin up and spin down, splitting of bands and spin up and spin down. In Rashba, you have helicity. That's a good quantum number. So this helicity that mainly appears because of spin orbit coupling of this type, Rashba and Dresselhaus thing.
Such a thing can also induce ferroelectricity in insulator, right? Possibly.
Ferroelectricity in insulators, yes, very nice. I mean, even I do myself. So for example, so you have when your system is close to ferroelectric transition, because atomic spin orbit coupling is always there, and when you are close to the inversion braking transition, the combination of spin orbit coupling and inversion symmetry braking, that gives rise to Rashba type of spin orbit coupling. That's very true. It's dynamical effect. But then when you are explicitly in the ferroelectric region, you have static polarization that gives you dynamical Rashba term and static Rashba term both. So yes, that's where, and even I work on that also. So that's where this happens. Yeah.
Okay.
Thank you.
Thank you, Abhishek.
Yeah,
And
thank
let's thank him for this nice presentation.